Go.
I'm Derek Stensel, and this is our final project here at the Mechatronics program at Alexandria Tech. This is the trap thrower. I was in charge of the design phase and most of the hydraulics, and then helped a little bit with the mechanical design.
My name is Zach Vold. I was in charge of the mechanical assembly.
I'm Cody Bruner, and I was in charge of programming and designing and installing the electrical aspects of what you see before you.
Alright, this is the mechanical design, a basic rough idea before we started building. Our design has kind of changed since then. Like, this top piece is actually now more of an I-frame, but overall functionality has stayed the same, and this is just kind of how SolidWorks moves, create all your components. So that is that portion of that. And then we also had to document our electrical circuits. This is basically where we're going from each input to an input module. This is the slot on the input card of our back-off terminals. And then we have a 12-volt power supply too for our solenoids and the pump. Then we also have hydraulic schematic. And this is the basic hydraulic. It's our pitch and rotation. This is our external valve. And this is what the schematic looks from the hydraulic pump itself and all the internal valves that it has.
Alright, this is the mechanical portion of our project. We did not build the trap thrower, we just built the frame. This is our base that swivels on some UHMW pucks we manufactured down here. This shaft in the center is what holds the whole thing centered. Then we've got this mechanical arm hanging off the side with the hydraulic ram that will turn the base left and right. For the up and down portion, we have this cylinder right here that pushes this top part of the base up and down. One problem that we had was this piece of sheet metal right here was too thin, so when this tried to come down, it just curled it like a taco. So we made this 1/2-inch steel plate and put it on top, and that took care of all of our problems there.
Alright, we use the Codesys Win V3 program to write our program. We use a combination of structured text and sequential function chart, which is what you see before you. Basically, we go through about 28 to 30 steps here, and each of which has an action associated with it, which is written in structured text, which basically has a list of your variables. And as you go through them, the inputs that will be fired on the actual project itself will determine what happens in the program.
Alright, what you're seeing here is basically the other end of what you saw with the program. We are feeding the program to what is called a bus coupler, in this case it's a back-off EK1100, through an Ethernet cable. What this does is it basically takes the input from the program itself and distributes that data through a series of input and output cards, being digital or analog. In this case it's just digital. We're feeding that through these breakout boards you can see in the back here, through a 25-pin D-sub cable to another set of breakout boards, which is in turn feeding those outputs to a series of EMRs which will fire the solenoids on our pump. We also have this power supply here. We're giving ourselves 24 volts, which is industry standard for this kind of technology, feeding the power to our bus coupler and to a set of connectors. And we've got a 12-volt battery that is supplying power to our pump. And that is the basic electrical schematic.
So we got going here, we rigged up a pump, which is actually a snowplow pump, and we have the basic function is up, down, left, and right, with down usually just being gravity feed. So we had to kind of modify that. We split that flow, and then it comes up to this other valve which powers our pitch up and down, and then our return we had a blocked flow path through port C3, so we had to modify this and tap directly into our tank. But the overall functionality now works just as we had hoped.
Another part of our electrical is these proximity sensors here. They have a sensing range, 4 millimeters, which is pretty close. But basically what happens is when each step cycles through, it moves until it reaches the current prox sensor that is written in the program. Say it needs to go up to prox 3, it'll ignore number 2, it'll go to number 3, and when it reaches that sensor, it'll actually stop for a predetermined amount of time, and it'll run through the next step. Say it'll move to this prox sensor after it has been at this one for 3 or 4 seconds, or in our case, it's 2 seconds. You can see, moved all the way up to number 3, completely ignoring the signal sent from number 2. Alright, the basic idea of this is to have it on the other side of the wall where the shooter cannot see what position it's moving to kind of keep you on your toes as to where, like as if you were hunting. You never know where the bird's going to go. Unfortunately, we cannot show you the trapdoor actually shooting at clay because we are inside and they go everywhere. But operation is basic. As such, you might be able to hear it going. You're never really going to know where it goes if you can't see. Cut.